Welcome, everybody, to RISE Learning Machines seminars. RISE is Sweden's public research institute, and I am Olof Mogren. I'm a research director responsible for the deep learning research area here at RISE. The computer science department works on applied AI projects for the benefit of society, and we organize these seminars every week. The meeting will be recorded, and if anyone wants to be removed from this recording, let us know. Also, do check out our collection of great talks that's been in this series on our YouTube channel. Today, I have the pleasure to introduce Alouette van Hove, who is a PhD candidate at University of Oslo. Alouette works with environmental science, aerospace engineering, and software development, and her research interests are among computational methods and applying machine learning techniques to address environmental problems. This includes reinforcement learning, Bayesian inference, and stuff, and estimating greenhouse gas fluxes using drone observations. The topic of today is aligned with this, guiding drones by information gain. And with this said, I will hand over the word to you, Alouette.
Oh, thank you very much for the nice introduction and for the invite to the seminars. I will share the screen. Did that work well?
Looks good.
Yes. Okay, nice. Yeah, so thank you very much for the invite to Edwin and to Olof, and I'm very happy to present my PhD research here. So my name is Alouette, and I'm working together with my supervisors Norbert Berg and Christopher Alstad. And I will tell you something about guiding drones by information gain. And from the title, maybe this is a bit vague, and what are we going to talk about? But we'll cover, as Olof already said, like Bayesian inference. We'll talk about reinforcement learning, drone observations, and estimating greenhouse gas sources. So in my project, all those things come together, and that's what I think makes it a very fun and interesting project. So what my supervisors and I are interested in is estimating greenhouse gas sources. So their location, but also the strength of greenhouse gas sources. And as a Norwegian university, we are primarily active in these kinds of areas. You can think, for example, about permafrost, which is soil which has been frozen for the past 2 years. And now with climate change, the soil might thaw because rising temperatures, which may cause cracks in the soil, which might cause gases which were previously trapped to actually get out, escape, and get into our atmosphere. And this is a process we don't know very much of. And this is something we're interested in, and we want to see if we can estimate this, get an idea how much this is. Now in Norway, we're also active in mires, so this is peatland areas. In the 50s and 60s, there were a lot of initiatives to drain those areas with the idea, okay, then we can do some agriculture there or forestry. But now the government is getting a bit back from this, and there are some initiatives to actually block those drainages again. So here was a little ditch, but has been closed off again, with the idea that the water table actually rises and that carbon will be captured in this soil. So then from being a source, it will actually become a sink of carbon, perhaps, but we don't really know how much this is, and there's a lot of uncertainty about it. Now, a bit more out of our comfort zone is agriculture, but we also are involved in a project where we look at emissions from ruminants, so for example, from cows. And if you look very closely, you can see the drone flying here above. So what we're interested in is how can we use a drone and observations that we can do with a drone. How can we use this to detect sources and estimate the strength of greenhouse gas sources? So we have multiple drones at our university which carry sensors, for example, methane sensor, CO2 sensor. We measure temperature, air pressure. And from those measurements, we want to find out, okay, where are sources of greenhouse gases and what is our strength? And the overall motivation of this is that we want to develop a framework using those drones that can estimate those sources, and hopefully we can then contribute to the validation and calibration of climate models. So if you have a climate model already in one cell, there can be a lot of processes going on, exchanging greenhouse gases with the surface. And we want to, hopefully we can, with our research, contribute to making the climate models a bit better and hopefully reduce uncertainties, which we now have in our climate change projections. So to show what we're actually are working on is that we have the drone, which is flying around. And this is measuring something in gas mass per volume air. But what we actually want to know is the source strength, so gas mass in time. So this is not a direct measurement. We need to do something to get from those observations to what we actually want to know. So in the framework that I'm working on, there are basically two main questions that we want to answer. And the first one is, how can we infer those surface fluxes from our drone sensor measurements? And the second question is, what is the best sampling strategy, or what is the best flight path for the drone? So in this presentation, I will present a case study to you in which we made some simplifications. So we say, in our domain, we say that there is one source. It is at an unknown location and it has an unknown emission rate, but we know that there is just one source. And we use synthetic data in the case study that I will present here. So one can look at the first question, and that is, how can we infer those surface fluxes from drone sensor measurements? Now I try to make here a diagram showing what we are working on. So we have the observations of the drone. This is something we measure, but we also have unknown parameters. This is the stuff we want to figure out. And we have our known parameters, for example, wind speed and diffusion. In this case study, we assume that we know those parameters. Now our problem is an inverse problem. So we will set up an observation model, and then with inverse methods, we try to estimate our unknown parameters from those observations that we make with the drone. And if you search for literature on this topic, if you search for source term estimation, then there's much more coming. Then you get some studies who work with this. So this is a term that is often used when we talk about greenhouse gas sources or gas sources or sources of odor in general. So in this case study, we'll talk about hits. So we'll talk about the discrete parameter, which are the observations. So the hits are, you can see that they are proportional to the number of detected gas particles per unit volume. So we consider this at our observations in this study. Now, if we look at a drone flying around in a domain, we can see that those observations are very noisy in general. And this is, for example, because of sensor noise, but this is mainly because of the turbulence in the atmosphere. So this is just the animation to show you that, if we do those observations, we get very noisy data. So we assume that the wind is coming from this direction and our source is somewhere here. But even downwind from our source, we can still have a detection of 0 hits. So this is also what we see when we go out in the field, that we have those eddies with information or eddies with concentration passing by, but it could also be that we're downwind and we just don't measure something for a little while. Now, so what we do is we take a probabilistic approach. Our model is not deterministic, but there's some stochasticity in it. So what we say is that our source location and our emission rate has a probability distribution. And in this case study, we consider it a discrete probability distribution. So this is how we'll show it in this presentation. So this is an example of a case where the source would be in a 5x5 grid, and we consider that there are 2 possible fluxes. And this is just a simple limited case to show you how I will show the probability distributions. Now, with our framework, we will want to update this probability distribution, so move away from the uniform distribution, but get to something which is a bit more meaningful to us. Now, for that, we have to set up this observation model. And in this case study, we use a model by Vergosola, which was published in Nature. And in this model, those hits that we talked about, those discrete observations, are generated by two parts. And the first part is a physical model of stationary advection diffusion. And the second part of the model is a probabilistic model of detection. So here you would see the solution of the first part of this model for a source which is here. So the first part of this model gives a mean number of hits that you can expect. Now, once you know this mean number of hits, you can come up with what the possibility is for the observations that you can get. So we draw those observations from a Poisson distribution. So we can compute with the Poisson distribution, we'll get a probability, for example, of 0 hits, given that our mean is this, 1 hit, given that our mean is this. And this would, for example, give us the following observations, given that this is the mean number of hits in the background. Now, what we can do is when we have this observation model, and when we have the observation, we can do Bayesian inference. So what I showed you before, this discrete probability distribution where I plotted the fluxes on top of each other, and now plotted those two fluxes next to each other. Those are the blue squares. So this is our uniform distribution. And on the left, we will see again this animation of the observations that the drone does, the same lawnmower profile. So what we'll do is we'll apply Bayes' rule. So we have, this is our prior. We'll get an observation. And from our observation model, we will know what is the probability to get this observation, given that we assume that our distribution is true. And then we get to a prior. So with each observation, we will sequentially apply this rule and update this. So what we'll see is that given those observations, the drone at some point will say, okay, the probability that my flux is 1 is very, very little. It becomes almost negligible. And then at the end of the path, it has decided, okay, my source is most likely here, could also be here, given the observations that I did. So this is the first part of the framework. How can we infer surface fluxes from drone sensor measurements? But in this example, we did samples in each of the grid cells. But what if we would go out to the field and the field is way larger and we actually have to decide where should we measure? And this is the second question that I'm focusing on. What is the best sampling strategy or flight path for the drone? So in this, so with this question, we can frame this as a belief Markov decision process. So we now say that our drone is in a certain belief state. It has a location, X drone. It knows for certain where its own location is, but it has this probability distribution about, okay, where do I think that my source is and what is the strength of this source? And this is the state of the drone. And now we say that the drone will have to make a decision about which action it shall take. So it will make a decision about going forward, backwards, to the left or to the right, or maybe stay in the same cell. It will update its position. It will receive an observation. It will apply Bayes' rule. And then again, just as we've seen in the animation, we'll get this update that the posterior will become the prior in the next loop we'll do. Now, in this belief Markov decision process, we're actually after a policy, so policy pi. And this policy is the mapping of belief states to actions. So we want to figure out a policy that says, okay, if I am in this state, if I believe that my source is maybe there, but also there, if the flux is maybe this, what is the best action that I should take? This is what we try to figure out. So now we'll compare two different methods. One method is called infotaxis. This is what they say is a nearsighted approach. So the drone will only consider the consequences of the next action it takes, and then we'll compare that to a farsighted navigation strategy, which we trained through deep reinforcement learning. So with the second one, the drone is hopefully able to see further ahead in the future and not only see what its direct consequences are, but also in the longer run. Now, how we frame those methods is that both methods select their actions based on something called expected information gain. So we'll have a look at what this actually is. So information gain is the reduction in information entropy. So we can say that information entropy is an average level of uncertainty. So here we have again this belief, and we start with this uniform distribution, and a uniform distribution has maximum level of uncertainty and has also maximum entropy. Now, completely on the other side, we have a probability distribution where all the cells are 0 except for one cell which has value 1. And this has a information entropy of 0 because there's 0 uncertainty in this probability distribution. So our goal is with our navigation strategy that we are devising is that we start here, but in the most ideal situation, we want to end up here. We want to have 0 uncertainty about what the actual source strength is and what where the source is. So this is our goal, to get to something that's as close as possible to here. So now let's look at those two different methods, and we'll do that for a test case where we consider 605 possible source scenarios. So we'll look at an 11 by 11 domain and 5 possible emission rates. And we say that the drone has a battery life, and we say, okay, the drone can do 20 actions. And we kind of want to optimize the information it can gather in 20 actions. Now, infotaxis was developed by Vergosola. So this it's from the same paper as this observation model was. And here you can see this a bit like the decision tree I try to visualize here. So the drone is in a certain state. It has the possibility to choose between those actions. And after it chooses an action, it will get an observation. And given the observation it gets, it will end up in a next state. So there are a lot of different states that the drone can end up in after it chose an action. Now, the expected information gain is the difference between the information entropy the drone has now and the information entropy the drone expects to have given the action it chooses. So based on its current belief, it can compute the probability that it will get one of those observations. So for example, it can look ahead one step and think, okay, if I will go left, then, and I think this is my current belief that this is the truth, then I think there's a 50% chance, for example, that I will get a hit 2, and there's a very little chance that I will get hit 0, for example. So this is again what we know from our observation model, from this physical part and then this Poisson distribution afterwards. Now our policy is to say, okay, we want to choose the action that maximizes our information gain. So we look ahead and we choose the action where we think, okay, here we can gather the most information. And if we combine those two equations here, we'll get to this expression. So this is the same for all possible actions. And here we have a minus, so we can go from max to min. And we end up with this expression. So here we will see an example of how this looks on our grid. So on the left, we have our 11 by 11 grid with the drone that is starting in the center. Now on the right, we'll see the action selection. So in green, I've plotted the expected information gain. So once the drone starts moving around the grid, you will see green cells lighting up, and you will see that the drone chooses to go to the cell which is most dark green, so which is the highest expected information gain. Now in the middle plot, that's the belief. So before we had those possible fluxes stacked on top of each other or plotted next to each other. This became too much of a mess, so I now summed over them. So you can see here in the middle, it's kind of the belief where it thinks that the source location is. So from this one, we cannot see what the drone currently thinks that the strength of the source is, but you can see what it thinks that where it thinks that the source is. So here you see that the drone will always select to go to the cell, which is most dark green.
Question.
Yeah.
The readings, so I suppose we're assuming a sensor on the drone here, and the readings, is that the scalar value?
So yeah, it's a discrete value in this case study. Yes.
Okay.
Yes. So those hits are 0, 1, 2, 3. In this case, where we have our 605 possible scenarios, we say, okay, the maximum amount of hits it can get is 8.
Okay.
Yeah. So this is a bit of a simplification in this case study. Yeah. So this is another one. And in this example, the drone gets very low hits. So what we see is that even at the end, so after 20 observations, the drone has chosen to take this path, but it still has uncertainty about where it thinks the source is. I think the highest probability is, I think, in this cell, but it still considers that all those other cells are possible source locations. But given that this method is just like used out of the box, it's used immediately without any training or something, it performs quite well, and it is able to estimate the location and the strength of the source in many of the cases that we tested. But now we're going to see if we can maybe even do better if we train a policy or if we train a navigation strategy through deep reinforcement learning. So we look at the same test case for this one. But now with reinforcement learning, we still have our setup of the problem, but now we have some other parameters that come into play. So we say that that's related to a state is a certain value function. So each belief state has a value. And this value kind of tells you how valuable it is to be in a certain, to be in this specific state. So each time that a drone goes from a state to a next state, it will get a reward. And the value function is the expected sum of future rewards when the agent follows a specific policy. So now what is the thing with the reinforcement learning is that we want to choose the actions that maximize the expected future rewards. So we get this expression for our policy. The drone tries to maximize the next reward, but it also wants to end up in the next state with a high value function. So which you say, okay, this is a position from which we expect to also get a lot of rewards in our future. Now in our study, the reward is based on information gain. So we said that the reward is the negative of the information entropy of the state it ends up in. And then we get to this expression. So we again do this thing that we have the minus here. So we go from max to minus. And we can now sum over the possible next states. And if we compare this to our infotaxis policy, we can clearly see that this infotaxis policy was nearsighted. It only looked at next state, but that was not. But in reinforcement learning, we look at the next at the reward, but we also look at optimizing, trying to get in a good position for the future, where we expect a lot of rewards in the future. Now, whereas this infotaxis could be used like straight away, the value function needs to be trained. So what we do with reinforcement learning when we train a policy, we say that the drone has this state, but it also keeps track of the value function, which you can consider as the memory of the drone. So the drone will gather a lot of experience. It will go through this loop many, many times. And each time it goes through this loop, it will receive a reward, and it uses that reward to update the value function. So it will use its experience to put it in this value function and use this information later. Now, what we do with the training, we train the drone over 20,000 episodes, so 20,000 flights. And in reinforcement learning, it works such that in the beginning, you tell the drone, okay, just take a random action, whatever you think is best. And then further on in the training process, you say, okay, don't select as often a random action, but select more an action according to what you have learned so far or what you have experienced so far. So select the best action according to the policy you've devised. So when we talk about exploration and exploitation in reinforcement learning, then it's referred to this process that we start with exploring our environment, but then later on in the training process, try to refine what we have learned so far. Now, after training, you will get to your optimal value function. So we can write our reinforcement learning policy, which we will use like this. Now, even though that we just have an 11 by 11 grid and we consider those 5 possible fluxes, we already have so many belief states, a huge number, that it's too large to do this, to compute those value functions exact. So we have to do that through a deep neural network. So this is a very simplified diagram of how this looks like. But our input will be the position of the drone and its belief. And then we have a bunch of hidden layers, and our output is one node. So this is this value function. And what we do during training is we try to alter the weights of our neural nets. So what we do with the training is we try to solve for the optimal weights by minimizing the residual error. So we start with an estimate for our value function, and with the Bellman optimality equation, we try to nudge those weights in such a way that this loss function becomes very small. And then once we have trained our neural network, we can now write our deep reinforcement learning policy like this. So we've optimized the weights in this case. So in our study, we have looked at 2 different neural nets. We've looked at a fully connected neural net, and we've also looked at a convolutional neural net. And both behaved approximately similar in our case for this study. So now we can compare our infotaxis policy to our deep reinforcement learning policy. So now we'll see in green, we'll see the infotaxis, and in purple, we'll see the deep reinforcement learning. So on the left, we'll see again how they navigate through the environment, and on the right, we will see the entropy and the cumulative entropy. So this entropy high was large uncertainty. So low values in this plot are beneficial. Then it means that the drone has become more certain about where the source is and what its strength is. So in this case, the true source is over here, and it has a flux of 3. So what we see in this case, if we go to the completed flight, we see that actually both the infotaxis and the deep reinforcement learning drone, they were able to reduce the entropy to 0 or to almost 0. And they both managed to estimate the location of the source and the strength of the source. So what we see is that what we see in their behavior in the grid is that they will search a bit, but as soon as they get observations, they try to move towards the source because there is the most valuable information for the drone to detect what its location and what its strength is. So let's look at another flight. So in this case, the reinforcement learning drone is able to detect where the source is and what its strength is much quicker than the infotaxis agent is able to. So even at the end, after 20 observations, the infotaxis drone still has some uncertainty about where the source is and what its strength is. So now if we define success as the drone's ability to estimate the correct source location and emission rate with a final posterior probability of more than a half, then we see that across all those different flux strengths, the deep reinforcement learning agent is able to outperform the infotaxis agents. So you can imagine the stronger the source is, the larger the plume is. So there are more observations. There's a higher chance that the agent will detect something when it's moving around in the grid. So the chances of success increase with the strength of the source. But we see that although we train it across all those 5 fluxes, we see that if we then just evaluate it for a specific flux, that the deep reinforcement learning agent performs better than the infotaxis agent. So what we see if we just go back to this grid is that when the drone doesn't detect any information, then we see that the infotaxis agent goes down, and then it goes to the sides, and then it goes up again. And what we see that the reinforcement learning agent does is that it immediately goes a bit off-center. It goes also down, so it will also go downwind. But then here it starts to make a sweeping pattern. So I think that's the big difference. What I could observe between those 2 strategies is that the deep reinforcement learning drone has learned to better search for information in the case it doesn't have any information yet. Because when you go here down and you would get some information, there's still an equal possibility that the source is here or that the source is here. And then over here, it goes to a corner where the chance for information is pretty small. So this is what I could detect when I compare those 2 methods. So what I've showed you so far was for a situation where we had a wind speed and a specific diffusivity. We also looked at other wind speed and other diffusivity, so we tried to change the environment a little bit. In non-isotropic conditions, so when we do have a wind speed, we see that a higher wind speed improves the success rate and lower diffusivity improves the success rate. So you can imagine that if you would consider it a stationary situation, then just the gradients, the concentration gradients within the plume are larger in that case. So I think that is easier for the drone to then search for where is the source or where is my plume and how can I go upwind to get closer to the source and get more information about its strength. And what I saw in isotropic conditions, for at least for the case study that we now looked at, is that sorry? Do you have a question? Maybe I'll just continue, but feel free to ask. So what I saw in isotropic conditions is that it was very difficult for both infotaxis and the deep reinforcement learning agent to say where the source location was. And I saw, we basically saw no difference between the two policies. But that is for the case study that we now looked at. So what I'm also now looking at is, for example, if we don't start the drone in the center, but maybe downwind and in a corner, maybe this is a way better starting position for the drone to start its search than in the center of the grid. So what is next is I really want to further develop this framework towards more realistic field scenarios because we've now set it up and it's working well, but it's still quite far away from that we can actually use it. So things like larger domains or different atmospheric conditions, that's mainly an issue of computational power. So to train more different scenarios. But what I'm working on now is to move away from those discrete hits to continuous gas concentrations, observations, and continuous flux strength estimates and locations. So that is what we just discussed, that those hits are discrete. It's like a hit 0, 1, 2, 3, 4, 5. And it's more natural to have this in grams per cubic meter. But this means that instead of having this discrete probability distribution, we'll go to continuous distributions. This means that we won't be able to use this closed form base, but we'll start using a Kalman filter or a particle filter. I've now been looking at an ensemble Kalman filter and it's working quite well. But then also in reinforcement learning, this looking one step ahead that we have now with our value function, that will be difficult to use, so we'll most likely move to state action values. So this is more like the Q-learning some of you might be familiar with. And then another thing to look at is how can we handle domains with multiple sources. This is I think a nice problem to work with in the future as well. So apart from this, the reinforcement learning and the case study, which is a bit more with synthetic data and further away from reality, I just wanted to show you a little bit of the field work we've been doing last month. So this doesn't include the path planning yet. When we look at the field work, we're more in the stage that we are trying to do this inference. So this is for this Circ Agric project. So this is for the project with the agriculture. So here we are. Here we are looking at how can we estimate the methane emission rate of ruminants from drone observations. So we were 10 days in the field we managed to do 19 drone flights. So we have a lot of observations or a lot of data. And we looked at different animals. So we had goats, sheep, different types of cows, male cows, female cows. And each time that we did a drone flight, those animals were in what they call the boma. So this is a very like a international project, and we had the chance to go to Kenya, where they do this practice of keeping the animals in a boma. And then we were flying there with our drone above the animals. So what we did was that we did some flights where we flew a box around the animals. We did this at different altitudes. We did flights where we looked at the wind direction, and then in the downwind direction, we kind of flew like a half octagon at different distances from the boma and also at different altitudes. And then we did those lawnmower profiles. So this is more a bit larger scale. I think this was like 150 meters. And we also did this at different altitudes. Now with those flights, we want to do this source term estimation. So the Bayesian inference we've been talking about in this presentation. And then we'll also compare that to literature values and to another method, mass balance box method. And this is why we did those drone flights. So from those first drone flights with the box, how that method works is that you take your measurements. Here we have our methane measurements, and you also look at the perpendicular wind speeds to the sides of the box. You interpolate them. So I interpolated them here to 1 by 1 meter cells. And then you can compute a local flux by multiplying the methane concentration and the wind speed. And then you can kind of have like a box where things are coming in and things are coming out. And the flux out is higher than the flux in. So we can say, okay, this difference is then caused by the animals inside the box. So this is one of the methods that we'll compare our source term estimation results with. And here I would like to look at different observation models. So the Vergasola model, which we used for the case study as well, Gaussian plume model. Both of them are fast computing models, but the question is, do they represent reality good enough to get a good estimate? Or maybe we should move to something more computational expensive, but more realistic, for example, an atmospheric large eddy simulation. So this is what I want to figure out with this project. Well, some like final thoughts about what I've been working on. I think we showed with our study that we can use information gain as a reward in reinforcement learning. This is something rather novel, I think. We saw with the case study that we did that we can actually outperform with deep reinforcement learning an infotaxis policy. But we'll also see that there are still like several steps needed to bring the path planning, the adaptive path planning, into a real life situation and fieldwork. But I've still got some time in my PhD, and it's very nice to work on this project the coming time. Yeah, thank you very much. Please reach out for questions, suggestions. If you want to discuss this, it's very easy to find my email or contact on the university website. Yeah, and if you're interested, you can always have a look at the paper about this topic. So thanks again.
Thank you, Alouette. These are really interesting things. I think meanwhile everybody else thinks about their questions, I'll start with a question. Could you use this approach with more complicated sensors? Say if you wanted to detect some kind of pollution using a camera sensor, for example. Would that be a stupid idea? That's the part of the question. And the second part of the question, would your approach be able to handle that kind of sensory input?
But with a camera sensor, you mean that we can visualize the actual plume?
Well, it would, yeah, that would be if we're measuring something that's actually possible to measure with a camera, yes. I suppose some kinds of pollution could be possible.
Yeah, I'm now thinking that
Exhaust fumes
if
from
it's like
traffic.
connected to color intensity or something, I
Yeah.
think we would have to have something to measure to say where it's like have a value of low and high within this camera. Yeah.
Mm.
Yeah.
So perhaps if we have a model for that, then.
Yeah. Yeah.
Um,
Mhm.
and then we have a few questions from Alexis, who is in our research group, and he had to leave early, unfortunately, but he's very interested in all these things. So there are three questions from him in the chat. Does anyone else wants to have the questions first, or should we go on with Alexis' questions? On with them. I'll read them so everyone can hear. The main challenges when going to real cases with in
Oh, sorry, you froze for me.
oh from it's to real world use cases with emission in space.
Oh, I don't know what's happening.
I think Olaf's internet connection was bad.
Oh, I hear you well.
Yeah,
Yeah.
you can hear me? Yes.
Yes, very
Then
well.
I can read a question instead then from the chat. So Alexis wonders, what do you see as the main challenges when going from the simulated settings you described to real world use cases with emission tracking in real 3D space?
I'm curious about if we can get away with using this cheap or computational cheap observation models. That would be the ideal scenario if we can use a computationally cheap model to do this, because that means that we can actually start doing things on the drone, like with a Raspberry Pi or something. But it needs to happen quite fast to be able to be adaptive in the field. But I hope with this second study where we just not look at the path planning, but to those measurements of the animals, that we can find out if those observation models are good enough, or if it will be
right.
Or if the uncertainty is very high and the results will then be less meaningful. Yeah.
Then he had a follow-up question on, have you considered training the deep reinforcement learning approach in a budget adaptive manner in which the budget may vary from scenario to scenario? For example, it might, for example, be doable by having the budget parameter as a part of the input state space for the agent, thus allowing it to adapt its search with respect to it.
I don't know if this is exactly what he means, but I did consider like that you have a budget which is like battery life, and that a step has a certain expense. So doing a small step is cheaper than doing a step maybe further away, but that it has those possibilities.
In the current framework, you mean?
I didn't consider it for this problem, but it is on the I wish to implement this list.
Right. Makes sense. Yeah, and then his last question was similar to the previous question. Does the deep reinforcement learning approach generalize to other grid sizes beyond, for example, 11 times 11? That is, even if it was trained only on 11 times 11 grid setups. Did you look into that, or?
I didn't look into that. I want to say that it's now restrictive to the domain that we set in the environment. Yeah, I think that's, yeah. I think that's what we have now is not, if I would suddenly say, okay, my domain changes, it's not 11 by 11, but my domain is now 31 by 31. I think I would have to train, do the training again.
Right. Okay.
To get a policy for that.
So that's maybe an interesting research question in itself, like how to generalize to other grid sizes if you train on a certain.
And that definitely would make it more applicable to use in different field scenarios.
Interesting. Thanks. And then we have a raised hand by Misha.
Thanks, Edwin. Thank you, Alouette. Very interesting. I guess I'm not frozen. I'm still formulating. Basically, it's an idea. The challenge with one drone and one sensor is basically what you are in 2D landscape is basically that you are trying to determine a distance using just one eye. I say I haven't thought it through, but I mean spontaneously I would say using two drones, probably two sensors on one drone would be not enough because of the diffusion, so the difference will not be large. But if you use two drones, you will be able to locate the source much faster if you correlate information from two.
Yeah.
I need to think it through, but I think so. It will be much faster because you will be able to calculate gradients much faster between the 2 points, and you know the exact position of the drones.
Yeah. No, this is something I've been looking at as well a bit, and also with the question how much information can then the drones communicate with each other. So we also have some people from the what is this? Work with wireless communication and such involved, because at some point we have 5 the same smaller drones which carry CO2 sensors. So one of our goals is to get those 5 drones into the air at the same time, and also that they communicate with each other and not have to go through the ground station. And then I've seen some methods where the drones can, for example, communicate with each other, just their belief. Also options that you can say, okay, let's share a belief together among those 5 drones. But then this is way more risky if one of the drones would drop out. So that's why people in practice say maybe it's better if they would each have their own belief and update this belief. And then there are also like variations. So there are a few studies with infotaxis where they looked at different methods about how can we let the drones cooperate. And there was also an interesting one where the drones would kind of like do a suggestion, say, okay, I think my best action is to go there. And the others would also come in with their best option. And then they would use this information from each other and reevaluate the choice they had made previously, and then kind of like go through this loop until they were all agreeing with each other about what the best next step would be.
But so technically, I would say engineering-wise, I think basically centralized solution may be even better, and it's totally implementable today. So you will still have a center to take the information and control the drones from the single center, but you can combine this information from the 2 drones basically, and give commands to the drones to fly and investigate certain areas.
So I have with the case study that I show now, I made a version where there are 2 drones which share the same belief, and that just can be handled by the cluster. But now I think when I go to those, there's also a reason to go to those continuous observations and this Q reinforcement learning instead of this one-step look ahead with the value function. Because when you add a second drone, then you have so many more possible observations and so many more possible actions you have to do this one-step look ahead for, that it becomes computational very, very expensive.
Well, I'm just thinking in simpler terms. Sorry to interrupt you, because it's I mean, having a few measurements from two separate drones will, I mean, even if your model is probabilistic, you still will be able to, say, compute gradient-like information from the two drones. So, and this will give you, say, just as my anticipation that it will give you, say, information where they should fly, to which direction they should fly to find the source quicker.
Yeah, no, I think so as well. If you have two drones with observations at the same time, it will, it will give a lot more information.
Thank you once again.
All right.
Oh, no, thanks.
Yes, thank you, Alouette. I'm frozen now.
Yes, now you're alive and kicking.
Oh, that's great. I was actually kicked out from the meeting. So it's good that the meeting didn't. And
I think I am a co-host, so we survived.
That's great. That's great. So I think with that, we'll say, well, thank you very much for this exciting talk. It's obviously of much interest for all here, judging by the discussion. Next week, we'll have Professor Tobias Anderman from Uppsala University visiting us. He's going to talk about spatial biodiversity modeling with remote sensing and AI. And this is in 1 week, April 18th at 15 in the afternoon. Welcome back then, and thank you very much for today.
Thank you.